What we're going to finish with is the parallel axis theorem. And remember when we did centroids and that sort of thing, as much as we loved integration, it was much more fun and much easier to do the composite approach, where we knew we could put a triangle and a square together and put in a round hole and do that sort of thing. Well, we can do the same thing with moment of inertia, but it's a little bit difficult in the sense that when we think about the centroid approach, it was y times a. So it's just very linear. We could do that. Now we got this y squared term that we have to deal with. So what we're going to find then is that there is a way of doing it, but it's just going to be a little bit different than what we did with the composite approach there. So the key thing, what the parallel axis theorem allows us to do, is we're going to use it to find the moment of inertia about any axis. And then, as I stated, what we'll be doing then is using it to create this composite construction. So things where you might think about where it's used is you'll see sections back in the older days when they had I sections and stuff, they were putting up I sections, you'd put plates on top and put a plate on the bottom. Well, the I section had a moment of inertia, but once you welded or bolted plates on top and the bottom, then you actually have a different moment of inertia, and you have to calculate that using this particular approach. So what we're going to do is look at a piece, and we'll just start off with a rectangle, pretty straightforward. And what we're going to want to do is look at this section, and we're going to take it down to this line AA, and we're going to want to create a moment of inertia about that line AA. Now, we know where the centroid of that is. And let me change that just a little bit. My y a little too far up there. We're going to take this, and when we do the integration, remember we used y in this particular case for our integrand there. But what we're going to do in this particular case is we'll define the distance to the centroid as d, and then this little extra piece is y prime. So nothing fancy there. Basically, the y that we were using before now will be composed of these two pieces. But when we think about placing it now in our calculation for moment of inertia, again, this y squared term kind of gets in the way. But what we're going to do is simply substitute that in there. Like so. Now, of course, before we can do any sort of integration there, what we're going to have to do is expand that squared term there. My D's are looking horrible here. So we're just simply expanding that term. I just multiply it out. Did I miss anything? So the d squared, I can pull that out, right? It's a constant. It's not changing. The y prime will change, so I need to keep that in there. And then the y prime squared will change also. Does that term look familiar? Can anybody? What? What's it doing with the centroid? But we actually did this calculation earlier. It was this thing, first moment of area, remember? So first moment of area was just simply the single moment arm there. There's no multiplication times that. But remember what the first moment of area is about the centroid? Hmm? No. So think about, if we're doing an integration, I'm going to do positive y to here, and then negative y to here, and add them all together. And it's just linear, so it's just y, positive y's, and a bunch of negative y's times a.
It'll all cancel out.
It'll cancel out. So it's equal to 0. The way we've laid this equation out, then, that term goes away because it's based at the centroid. It's measuring from this point here now, the centroid, and it's going to go up and down. Positive quantities and negative quantities, since there's only the linear term there, will cancel out.
It's only if it's uniform density.
Uniform density, yeah. Mm-hmm. Yeah, as a matter of fact, centroid and moment of inertia, that's a really good point to think about. The centroid and moment of inertia, we have to deal with the same density throughout the whole thing. If we deal with something different, then you get to learn that in mechanics of materials. There's the transformation you get to do there. So you're thinking a couple of courses ahead, but you'll get there. Okay, so what that leaves us with then which is basically what we call the parallel axis theorem. So just some definitions. Okay, so IAA basically is going to be our unknown moment of inertia about some axis. I bar then is going to be the moment of inertia about the centroid of the section, which we'll find basically in the back of our book. Lots of sections are already defined for us, and that's, again, how we're going to do the composite construction eventually. A equal to area. And the troublesome term and the one that people miss the most basically is going to be that D term. Now, what you'll see why the name makes sense is parallel axis theorem basically means that I'm going to be doing a parallel axis. So I have a centroidal axis here, x or y, in this particular case x. So my parallel axis theorem says that I can find the moment of inertia about any parallel axis that's parallel with x. So I can go down to AA, BB, whatever. Now I can't switch that vertically or go 90 degrees and that sort of thing. It's only going to work on a parallel system. But I can do the same thing for y. If I have y, then I can create moments of inertia based upon that. And again, we talked about, remember those radius of gyration, basically. Again, the steel folks like to use that a lot. So what we can do is just simply rewrite that and then simply substitute it into this formula here. And the one thing we'll note is there's a common term across that whole set there, so we can drop the a's basically. Again, so what we're saying then is if I need to calculate the radius of gyration about some other axis here, basically all I need to do then is this same form here. And the same definition there, basically. So the one is the one that's about any axis, but we need to have the radius of gyration about the centroid before we can apply this formula. Again, we can do it with the polar system. And again, our constraint there is going to be that centroidal. So we need to have that centroidal before we can apply this. Okay, so there's two different ways we'll be applying this. Form 1 basically is the one that we just got done writing. So any axis basically says then I need to know the centroidal moment of inertia before I can do anything. I need to know that, the area, and then I need to be able to measure from that centroidal axis to whatever one we're looking for, this new axis system that we're going to. We can also rewrite this just simply swap the terms there. And what we can find is that what this form says, then if I have a moment of inertia about some axis, and I want to find it for the centroidal of that, the centroid of that particular section, I can just simply write it the other way. And the point I wanted to go there was the point you made the other day there, is that proves, this is another way of looking at it, the I about the centroidal axis will always be the smallest. We saw that from the integration the other day there, but simply just looking at it in terms of the parallel axis theorem, any other axis system is going to be bigger than our centroidal axis system. Okay, so simple formula. What we're going to do then is use this to create those composite sections then. And that's the second portion. So again, this is just going to be our tool for basically looking at built-up sections or sections that are composed of a whole bunch of different pieces there to get an idea of its resistance to bending. And just like the centroid approach, in terms of using those pieces there, we generally have the I bar for simpler sections, just like we had the centroid for those. And then we'll just simply do an application of our parallel axis theorem here for the new shape. So we'll just go ahead and start off with examples and look at both forms here, approaches to both forms. Color's dying on me. Okay, so recall when we did the rectangular shape, the first thing we solved and then the other one we solved was about the base, remember? So we solved both of them. So what we're going to do is just apply the parallel axis theorem and see if we actually get that. So solving for Ix, So I put in my I bar that I know. So that's the thing generally I can pull out of the book or the text or Steel manual or whatever. Area is going to be BH. And then G is going to be this distance here. It didn't show up too well, but basically H over 2. But it's squared. And when we just kind of walk through that math, what we'll find then is then the BH, we have h cubed there, we'll have an 8 there. And did I lose it? No, that'll be a 2, sorry. 4. Just simply, that'll be, another way of expressing that would be, what, 3 over 12? So 3 plus 4, 4 over 12 divided by 3, then we end up with the same term. So nothing exciting there, but at least it checked to make sure that that particular base formula that we calculated through integration was correct. Now an interesting one we have in the back of the book, we have a semicircle. But the author didn't give us that information from the centroid. So in the back of the book, in the text, we're given that. But that is based upon a moment of inertia about this x-axis there. So one of the issues I have is I can't use that in the parallel axis theorem, because if I need it in the parallel axis theorem, I need I bar. And just to get some details out of the way here, A, which I haven't got up there yet. So the distance A up to that centroid is given in the book. Real nice term, 4r over 3 pi. And then the other bit of information we have from that is, know what the area is. It's going to be pi r squared over 2, half of a circle. Now what we can do is use that form 2, however, to get us that I bar. So what we'll do is we'll set up our expression. Like so. So we'll use that second form there, and then just plug the values in. So we've got the value at ix. We'll go ahead and plug that in. Over 8. And then we'll plug in the area. And then finally, this distance A from the x-axis there up to that centroidal area there, we need to plug that in. But then we also have to square it. And then what we get is this yucky term. Pi ended up being there in the bottom. And what we'll find then is the moment of inertia for a semicircle is going to be that. And actually you can confirm that because for some reason other statics books gives you it, why our author doesn't. But again, the point is if you've been given a moment of inertia about some axis, and you're going to be maybe putting this on a composite. There might be the ice cream cone that we did in one of the exams there. We might need to do that. What we can do is simply do a two-step process, use that form 2 to get us the moment of inertia about the centroid of that section, and then finally add it to some other pieces that we need. Okay, now we'll do a little more complicated shape here. I'm going to put this over here and hopefully leave it up. Get my pretty colors here. So basically what we have when we take a look at it is we've got a rectangle there, we've got a semicircle placed on the end of it, and then we've got a hole cut out. So let's make sure we think about what the shape is then. It's going to be this hatched area here. So as I mentioned, basically it's a rectangle, a semicircle placed on the end of it, and then we cut a hole out. So we've got a 20 millimeter radius hole, we've got a 40 millimeter bend in that, and then our section there is going to be 120. So what we're going to do now is just take a look at each piece and see what information we have on that. Easiest one is our rectangle. We'll call that 1. My colors are way over here. Oh. And I guess the key thing is what the heck do you want out of that? What we're going to be asked for is to find the IY about that section. So one of the things you always have to be careful is just make sure which direction you're looking at there. So our Y direction is vertical. And we know the centroid of the rectangle. And the nice thing is the X goes through that, so we don't have to worry about that. And then other terms that we need. It's 60 millimeters to the center, to that centroid. 120 millimeters along the length there. And then what's the height here? 80. Yep. 2 times the radius. So they like to throw things at you too like that. Okay, so key things we're going to need. We need the area. And again, keep your dimensions there. So just simply that. And then we need the moment of inertia about the centroid of that axis to be able to apply my parallel axis theorem. So I'm going to use the BH cubed over 12 portion.
I think your millimeters is squared.
And I changed that too. Oh. Yep. Area squared. And we always end up with really nice big numbers. This one is to the fourth. Now, one of the key things when we start looking at the other piece there, we have to measure this all with respect to the axis system that I'm trying to do. So I'm trying to move it to y. Question?
For that box, is the length 120 or 100? 120.
20, sorry.
Is this 120? If the length of the box is 120, wouldn't there still be a semicircle in that rectangular box?
No, it's 120 here, and then I slap the semicircle on the end there.
He means like you're including the, he doesn't say you're going to subtract out that small eventually. Not yet. Oh, we're going to add that. He's going to subtract that out later.
Yeah, I'm going to subtract that out. Yeah. So I'm going to look at all the pieces, and we're going to do the whole similar. That's a good point. What we're going to do is the whole similar to what we did with the centroids. We're going to create it as a negative area, is the key thing, and a negative moment of inertia too. Okay, so again, getting back to this one. Again, remember the centroid of that particular piece there is going to be 4 pi over 3r. And the one thing I'll note is this is going to be our D1, right? Because I'm measuring from the axis of y there to the centroid of that section there. So that's going to be my first D. My second D now is going to be composed of this length here, and that's one of the terms we'll get out of the way there. D is equal to that 120, which is the whole length of that rectangular section there, then plus the 4 So that particular piece, and actually we need to.
You wrote 4 pi over 3r, and then you put 40 times 4r over 3 pi instead. Yeah.
Oh, you're right. I'll emphasize that by putting it in black. And the one thing we didn't put up here, but the D1 is 60 to that axis. So that's the 3 things we need to get in terms of using that equation is the D, the A, and then the I naught. So finally, we'll go into hopefully I'll remember to keep this squared. So we just simply calculate the area there. And the nice thing is having done the problem before then, we've already got our I bar for that section. Oops. And that was the thing that we just got done calculating in the previous example there, is that I bar. Oh, and I'm switching names on you here, so your author uses the y prime. But basically, that's that y bar, the centroid, the moment of inertia about the centroidal axis. And then finally, and that'll be our part 2. Part 3 will be our hole, and again, we want to draw it with respect to the axis system that we're using. And we know where the centroid of that circle is, a pretty simple one there. So our distance d is just simply going to be that distance from there, and note that basically the edge of what that rectangle would have gone through is going to be there. But again, we'll put it up. And then pi r squared is going to be our area. And the moment of inertia about its centroid from the back of the book is 1/4 pi r to the 4th. And then we end up with a big term, but that's the moment of inertia about the centroid of the circle.
Are all these off the table? Are all these off the table, the radiating and the moments of the centroids? Or
Every one except for this one. This is the one that we actually had to calculate. But yes, this is from a square, so it's just bh cubed over 12. The other one, 1/4 pi r to the 4th, is in the back of the book. Yes. Although it might make a nice final problem, don't you think? OK, so what we're going to do is then set up a table. We've got 1, 2, 3, 4, 5 columns. Give yourself enough room. Yeah, I just want to throw you guys and see if you are awake. How am I doing?
You're doing great.
OK, so basically all we're going to do is just set up a table like we did with the centroid approach there. We're going to have some bigger numbers here. Yes, when we get to moments of inertia, we're talking big stuff now. None of this. So what we'll do is just simply take those. These are the ones that we just got done calculating. So we establish those on the table there. Nice Excel problem here. And then do the calculation for I bar plus AD squared. Our semicircle, a little bit smaller, but still now, interesting thing to note here, semicircle is so much smaller in terms of area, but look at when we place it way far away, boy, it's going to do a lot of resistance to bending. It's going to keep that plane from wanting to rotate more, the further I put it out. And again, that when you'll see that in mechanics of materials, you'll see that why we want to move things like in I-beams, move the material out to where the stresses are. And finally, 3 is going to be our tricky one, because that's the hole. And again, we need to put in a negative area, because think about that when I sum that all up. I'm sorry, that's negative moment of inertia. So it's going to be taken out of the system there. This is my area. Jumping a little bit ahead there, but when I add that column up again, what I should expect to see is the area of that whole section. And even that little hole has a pretty big number when we get done with it. So what we're going to do then is just simply sum up the 2 columns that we're interested in. So that should be the area of my section. And this is the thing I'm most interested in. Anticipation. Not going to break into song here again, are we? So our IY for that particular section, now notice how much bigger that is than any of those individually there. But when we add them up, and then area going to be equal to that particular piece there. Now, one other thing, again, if you're a steel guy, you're going to want to know the radius of gyration. And we just simply go and approach it via that form. We've got the 2 pieces right here that we need to solve for that. And what we'll find then is doing that quick calculation there that it'll be 83.3 meters. So what that's telling us is if I took all of this area, 10,856, and put it on a single line out here to get the same moment of inertia of this particular section, it would have to be about 80.3, about a third of the way across this section here then. So out in there would be that long strip of the same area, but it's going to be that far away to create that same moment of inertia, that same resistance to bending.
Is that kind of like the resultant forces when you have like you're calculating the centroid of something? You say, oh, this is like how that would act, like from this centroid, like when you were doing underwater, like the pressure and stuff. We said this is kind of how it's acting. Would you have something similar for this? Where it's like we can assume that it's acting just at that one plane.
That's, yeah. When you think about that internal couple, you remember we drew that internal couple there? That's that sort of thing. All your force is acting at that level. If you want to do it.
Put it as a resultant, like torque kind of.
Yeah. Yeah. And that's how the steel folks like to look at things. But now that's giving us the moment of inertia about that particular thing. What we'll do is we'll get started, and what I'll probably have to do is post the rest of it. What you'll be interested in is, okay, let's find the moment of inertia about the centroid of this particular section here. Okay, because you might want to take this particular section and then put it onto something else and have to do another moment parallel axis theorem. Well, in order to use the parallel axis theorem, I'm going to have to find the centroid of this particular section and then calculate the moment of inertia about it. So the approach is something we've already done. Find the centroid of that composite. And then the second step is our d's will change. So area won't change, but we're going to change our d's, because what we're going to do now is find a axis system that's going to be somewhere here in the centroid. And this is kind of a review, but not a bad thing to review. Centroid, same sort of table. Yep. I haven't left this problem. That's why I'm leaving it up on the board there. But good question. Yeah. So I'm finding, what I'm going to do is just simply find the moment of inertia now for this whole section. Because I want to take this section now. I built this, and I'm going to plug it onto an I-beam or something like that. Basically, same approach. We've got most of the data out of the way. So same area there. We've done that before. The only thing that'll be different now is that we're looking at first moment of area. So this is our first moment of area. Remember, just simply the x bar. So what that's telling me then is the centroid of this whole system now is going to be basically somewhere in that area there, about 71 millimeters over from that y. Then the key thing is what I'm going to do is reconstruct this through the parallel axis theorem. But what I'm now going to do is use these new d's. I need to calculate a d. I've got the centroid of this section, but now I have to measure it to the centroid of the box section, the centroid of the circle, and then the centroid of that. So my distances now so we'll call that d1 prime. That's the distance from the centroid of the entire section to the centroid of that rectangular section. d2 is going to be from the centroid of that entire section, that's 70.8388, to the centroid of that semicircular section. And then finally, d3 will be that distance. We'll just do the calculations over here real quick.
What's D2.
That's a semicircle. So it's the measure from the centroid that we just found of the whole thing to the centroid of that semicircle. Remember, that's that 4r over 3 pi. And with that, we can go back into the same table. And we won't do that. I'll post it on the web there so you can take a look at it. But all we've done is then just simply changed my d's. And what I'm going to do is create that same table that we did for the moment of inertia, except now I'm going to substitute in my new d's. And what that will do is then calculate the moment of inertia about the centroid of this section, which then we'll publish in some table somewhere, so the next person that wants to take that and plug it onto something else, they'll have that set. So I'll go ahead and post that.
Quick question.
Sir.
So the 10 is negative, so when it's squared, it's going to become positive, so does that like not really matter?
Doesn't matter, yeah. Good point, yes. Remember, yes, our d's are squared, so it doesn't really matter whether it's positive or negative when we plug it into the equation. The one thing that does change is going to be that area and the moment of inertia. We're going to put in a negative for holes in those particular cases.